Good afternoon, everyone. Thank you for the opportunity and this presentation. My name is Toshiyuki Nakamura from Gifu University. And I also participated in a similar seminar in Bangkok 2 years ago. And at that time, it was a relatively small seminar. And so I'm quite surprised to see such a large number of participants and this time. And today, our study titled Unstable Factor in OD Traffic Volumes are Variance Structure Analysis of the Nagoya Expressway. So before I start my presentation, and I would like to make a brief note. And this study has just started last year, and we're still in the early stage of the analysis. So why? The results are still preliminary, and I would greatly appreciate your feedback, especially on the methodology. So why and also, this research has been mainly carried out by Mr. Izuka, a student at the Gifu University. And with that, let me begin with the background of this study. So, traffic system inherently and variable, and understanding this variability is crucial for effective transportation planning and operating. Why? And diurnal patterns such as morning and evening peaks are well recognized. And there is a growing need to understand day-to-day fluctuation and instability in demand. So, however, conventional data sources such as road traffic sensor survey are constrained by their limited frequency and scale. And as a result, they are not sufficient to capture the dynamic and unstable nature of the traffic demand in real-world conditions. So, today, we are in an environment where data can be collected continuously and 24 hours and a day, every day, year, over a long period. And in highway system, multiple data sources are available, such as a traffic counter and etc. Transaction records and Prof vehicle and data. And these diverse data sources provide new opportunities to better understand traffic and variability and dynamics. And this study focused on origin destination OD data collected on urban expressway. Especially, we analyze daily OD traffic volume using data from the Nagoya Expressway network. So the object of this study is to clarify the mechanisms that generate instability or variability in total traffic volumes. And to achieve this, we use daily OD traffic volume data from the Nagoya University network. In particular, we focus on the variance structure of distributed OD flow, and rather than simply their mean levels. And by doing so, we aim to identify how variation across individual OD pairs contribute to the overall instability of traffic demand. So this analysis has 3 key features. And first, we characterize the structure of variability in distributed OD flows and capturing how fluctuations differ across OD pairs. And second, we quantify how these variations contribute to the variability of total traffic volume. And finally, we aim to reveal the underlying mechanisms that generate instability in network level demand. So, this is a research flow. First, we organize and process the data, and next, we conduct a basic analysis to understand the characteristic of traffic variability. And based on these findings are nearly defined indicators, we conduct a model to represented in stabilities. And finally, we identify the factor that contribute to instability in total traffic volumes. So in this study, we use daily intersection to intersection OD traffic volume data from the Nagoya University, the Nagoya Expressway network, covering a 1 year period from April 2024 to March 2025. The analysis is conducted at the route level, including 9 routes and a total of 81 OD pairs. In addition to traffic data, and rainfall data are incorporated as supplementary information to account for external factors affecting demand. The figure on the right illustrated a simple representation of the Nagoya Expressway network, and at the center is an inner ring road, and 8 logical routes extend outward from it. And note that in intercity expressway showing the gray, and this one, are excluded from the scope of this study. So in the basic analysis, we aim to identify the factor influencing traffic demand variability. And I applied autocorrelation and coefficient of variation to capture temporal patterns. We use analysis of variance to evaluate difference across congestion, such as day of the week and holidays and rainfall and special events. So, and first, we examine the periodicity of traffic, total traffic volume over 1 year. Why? And some irregular fluctuations can be observed, and particularly in early May, August, and December. And the overall pattern shows a clear periodic trend. And specifically, the interval between peaks and troughs appears consistent, and suggesting an weekly cycle in traffic demand. To evaluate this periodicity, we further conduct autocorrelation analysis. So, to analyze a temporal pattern in total traffic volume, we use the autocorrelation coefficient. And this measure indicated the strength of the relationship between past and plural value. From the result, we observed high correlation at leg of 7 of 14 days. This suggests the presence of weekly and bi-weekly periodic pattern in traffic demand. And based on the findings, we further examine traffic variations by day of the week to better understand these cyclical behavior. And next, following the periodic pattern identified in the previous slide, we further examine variability by day of the week. We use the coefficient of variation, which represents the rate of standard deviation to the mean to evaluate the level of instability. And the results show that holiday exhibit the highest variability, and this is likely due to difference in travel behavior and holiday timing. And Wednesday showed the lowest variability and indicated more stable traffic condition during the midweek. So these findings confirm that the day of week effects play a significant role in traffic demand variability. And here we present the result of the analysis on construction impact using ANOVA. From the result, we observed that traffic decrease in the segment where construction take place, and at the same time, traffic increase in adjacent route, including routing effect. Looking at the figure, the vertical axis shows the relativity difference, which represent how traffic change on special day compared to a normal day. And we can that significant change are concentrated in specific OD pairs, and particularly those directly connected to the construction area. Main OD pairs show no significant difference, suggesting that the impact does not propagate across the entire network. And the effect of construction is mainly located, affecting a nearby route rather than the whole systems. And we summarize the result of the basic analysis. And due to time constraints and many detailed results are omit, but the key finding of this basic analysis are presented here. And we find that day of week and weekday and holiday difference are long holiday period a significant factor affecting traffic variability. And construction effect are located. Rainfall does not show a significant impact on total traffic volume. And based on these findings, we propose to model development using the identified significant factor. So in this study, we defined the model that represents total traffic volume using both the mean structure and the variance structure. So the mean structure represents the baseline level of total traffic volume and incorporated temporal factor identified in the basic analysis, such as a day of week and holidays and the specific days effects. Then we focus on deviation from this baseline. The variance structure is designed to capture these deviation based on the variability of distribution or the flow. So next, I will explain the four variance components that characterize traffic instability. And first, the OD specific deviation indicates how much each OD contribute to overall instability. And a larger value, this one, a larger value means that the OD and this deviates more from its average level. And second, the concentration index represents how traffic demand is distributed across OD pair. And a third one is a cross-section variance capture a difference among OD flow within the same days. And finally, the moving window variance reflects short-term fluctuation. And each of these indicators captures a different aspect of traffic instability. So, and first I will explain the OD specific deviation. And this indicator how much the traffic volume of each OD deviates from its typical level. For example, and if an OD user has a traffic volume is 10 vehicles, but it included 30 on the given days, the deviation is 20. In this study, we use the absolute value of the deviation, and this is because both increase and decrease from the average contribute to instability. And by taking the absolute value, we focus on magnitude of the fluctuation regarding of its direction. And by introducing this measure into the model, we can identify which OD pair contribute to the instability of total traffic volume. And in other words, this indicator allow us to pinpoint the source of instability within the network. And next, I will explain that concentration in terms at a given time t, and so total traffic volume is distributed across the multiple OD pairs. So, for example, suppose the total traffic volume is 27 vehicles, and a large share of this traffic is concentrated in a specific OD pair, such as OD3 is maybe 15. In this case, the OD composition is in balance, and the value of the concentration index becomes large. By introducing this term, we can evaluate how much traffic demand is concentrated in limited number of OD pair. In other words, and this indicator captures the degree of dependency of total traffic on specific OD pair. And next, I will explain the cross-section variance. And this indicator measures how much traffic volume differ across OD pairs within the same days. And for example, suppose that at the time t, and the average traffic volume across OD pairs is 22 vehicles. We then examine how far each OD deviates from this average. And if the difference from the average are large, that cross-section variance become large. By introducing this term, and we can capture the variability among OD flows within the same days. And in other words, and this indicator reflects has uneven the distribution of traffic is across OD pairs at a given time. And finally, and I will explain the moving and wind variance. And this indicator measures how much traffic at that t and deviated from the recent average. And specifically, we compare the traffic volume at that time t with the average over the past L days. And in this study, we set L equals 7 and 1 week, and based on the weekly periodicity identified in the basic analysis. For example, if the deviation from the recent average is 19.3, and these indicators are a large short-term fluctuation, and when this deviation become larger, the value of the moving wind variance also increase. By introducing this term, and we can capture short-term and disturbance and fluctuation in traffic and demand. And this captured a short-term shock in traffic and volume. So, and next I will explain the estimation and method. And in this study, we include a large number of explanatory and variables, particularly in 81 OD specific and deviation terms. When dealing with such a high dimensional setting, and there is a risk of multi-curiosity and redundancy variables. So, and to address this issue, we applied Rust regression model. And Rust is a regression method that performs both an estimation and the variable section by shrinking an insignificant coefficient to 0. And using this approach, we extract the key factors that contribute their effects using multiple regression analysis. And last regression allows us to identify the truly important drivers of instability. So, I present the result of the last regression, and by applying last regression, we can extract the key variables that influence traffic instability. The result suggests that instability is not driven by all variables, but rather by a limited set of important factors. In particular, deviations in specific OD pairs and concentration and related measures appear to play a central role. Although the estimate coefficients may include some bias due to the nature of lasso, and this step allows us to identify the dominant drivers of instability. And based on these selected variables, we then conduct a multiple regression analysis to evaluate their effects in more detail. And instability is not random. It is driven by a small number of the key factors. So, finally, I present the result of the multiple regression analysis. And first, and for OD specific deviation, significant efficiencies are observed in 30 OD pairs, and this and 30 OD pairs, and both possible positive and negative coefficients are identified, and suggesting that some OD pair increase instability, while other help stabilize the systems. And second, the concentrate term shows a very strong and positive effect with a coefficient of 441. And this indicates that the concentration is a measure and driver of traffic instability. And in addition, several other factors also contribute to instability. And overall, these results suggest that traffic instability is not caused by a single factor, but is formed through the interaction of multiple components. And so, instability is primarily driven by concentration and specific OD deviation. And finally, I will conclude this presentation. So, the objective of this study was identify the factors that drive instability in total traffic volume. From the basic analysis, we found that temporal factors such as day of week and holidays and long holidays and have significant effects on traffic and variability. From the model-based analysis, we found that concentration strongly increases and instability, while OD specific deviation can either reduce it. So we also confirm that moving window and variance capture short-term fluctuation in traffic demand. And overall, these results suggest that the traffic instability is determined by the interaction of multiple factors. So by focus on the variance structure of the OD traffic, and this study provided a framework for more effective traffic management or analysis. So as future work, we plan to incorporate additional external factors such as weather and incidents, and to further improve the model accuracy. So understanding instability is the key to better traffic management. That's all. Thank you very much.